Try this again. I don't know why I did that. Maybe I didn't like the display settings I had. I have no idea. It's weird. Yeah, and also could be possible I didn't like the fact that I changed the displayed settings in the middle of the recording. Maybe, I don't know. Try this again. See if it'll die again. That'd be great. Like I said, I just need an excuse to buy a new computer. Said that the other day, didn't I? All right. Try this again. I like typing things in multiple times. All right. E3 squared divided by E5 plus E4 squared divided by... No. Okay, I know. I hit the wrong button. Get off me. Divided by E6 squared divided by 1 divided by E3 minus 1 times E3, oops, not E3 minus 1, it's E5 minus 1 times E3 squared divided by E5 whole thing squared. Yeah. You do have a blue screen. Try that. Probably because I unplugged it. Hey, is that better? Sorry. Jeez. I'm glad you said something because I would have just kept typing and talking. Seriously, definitely would have completely just kept going. All right. Plus 1 divided by E6 minus 1 times E4 squared divided by E6 squared. And I should just need one more to finish off. Yeah, one more to finish off. I should have went on it. Okay. Oops, there's a problem. I forgot my squared there. All right, so if you want to know where this formula is, it's on page 295 in section 6.3. Again, we're using this if the variances are unequal. We have to use this big, long thing to get the degrees of freedom. Oh, I know what else I forgot. I didn't put the floor in, did I? There we go. So again, the floor rounds it down. This is the Excel version of the formula that's on page 295 if I've typed in everything correctly. 8. Woohoo! That was exciting. I don't know what the heck happened. I'm using a different screen recorder in this case because the one I was using before automatically uploads it to that Nomia site. If you go to there, this will just create an MP4 and I'll have to either put it on YouTube or something along those lines. So, not that that's a big deal. My guess is you don't even care, but that's okay. All right. So, again, now to get our the difference of means standard deviation estimate, we have to do the square root of the sample variance divided by x size plus sample variance divided by y size, and then the square root of that. Plus we need the t value. So let's do the t value first. So we'll do t sub the alpha over 2. In this case, we'll do the t dot, if we can see it here. You want the t dot distribution, the inverse one here. Either the inverse or the inverse two-tail. It literally does not matter which one you use. If you use the two-tail, don't divide your probability in half. The two-tail will automatically divide it in half for you. Okay. So T dot inverse. I like to use the inverse instead of the two-tail because they don't have that option for the normal distribution. All right, so the probability is, this was exercise 6.3-4 in your book. And they want a 95% confidence interval. So I'll use the 0.975. The degrees of freedom are sitting right there in E8. So we get 2.306. Okay. And then we need the left and the right endpoints. So to get that again, we're going to do the difference of the two, which is E3 minus E4. We will subtract the T sub alpha over 2, which will be E9. And then the rest of this is exactly like what we did for the large sample size. Okay? Since we don't have a pooled variance, since we don't have the assumption that we have equal variances, we can't use the pooled variance like we did before. Okay? So all we're going to do is do this exactly like what we do when we have the large sample size. You're going to do the square root of the sum of the variance estimates. Again, we're assuming they're independent, so you would add the variances, right? So this will be the square root, SQRT, of, we'll do E3 over E5, E3 squared over E5, and then plus E4 squared over E6. And that's exactly what we did for the large sample, right? Do the square root of the sum of the variance estimates. And again, the reason why we're using this instead of the pooled variance is because we're not making the assumption that you have equal variances here of the two populations. Okay? So let me highlight that before I hit enter.
So we do the standard deviation instead of the mean at the end of this one?
Oh, did I type in the wrong thing? Yep, I did. Nope, thank you. E1, E2, you're right. Thank you. I had typed in the wrong thing. That was interesting. God. I should just quit today. Copy. Escape. Paste. Change to a plus sign. That's all I wanted to do. Thank you for noticing that, Aaron. All right, cool. Okay, so there would be our confidence interval in that case with our lower and upper bound. All right. I'm not sure that was any faster with me having the data typed in ahead of time. Of course, when you have the whole thing crash in the middle. All right. Again, the only difference between this and what we did last time was that we're assuming that we're not assuming that we have equal variances, so we have to use a slightly different formulation for the degrees of freedom, rather than just doing n plus n minus 2. Like I mentioned, if you're going to need to do this on an exam, I will give you that formula. There's no reason for you to try to memorize that big long formula. That's a waste of brain space. And I'm sure you need that for, I don't know, song lyrics, for example. Baseball statistics, I don't know. The unladen airspeed of the airspeed of a unladen swallow, something along those lines. All right, let's do one of these with paired. Any questions on that before we do one of these with paired differences? All right, so again, paired differences, no big deal. So this is exercise 6.3-11 on page 300. This is percentages of body fat. The first set of values are for males. The second set of values are for females. This is change in body fat percentage over the course of a semester by participating in a fitness program, a health fitness program, it says. All right, so if we just, there are paired differences. You've got a before and after. So that's why you would use this particular formulation if you're doing this for a statistical analysis. You've got the same number of data points. Each one has to be for the same individual object, whatever you're doing for the observation, right? Don't assume that if you've got same sample size for both, that you're doing paired difference, okay? You're literally doing a before and after. It's an observation. They're not random anymore, right? You might be randomly selecting one to get a sample, but you're using that same sample you started at the beginning and remeasuring at the end. That's no longer random for the second one, right? So in this case, the first thing you do is calculate the differences. So in this one, I would just do, let's say I do A1 minus B1. Again, the left two columns are males. Okay. Oops. Yeah. Well, let's let me grab it. So there are the 10 differences for the males. And now you treat that as a single sample and do what we've been doing. Okay? We've got one sample. You would calculate its mean, calculate its standard deviation, find the degrees of freedom, which in this case would be 9, right? And do the same thing we've been doing. Okay? So if you wanted a confidence interval for this, like I said, this is not a big deal. You just have to do the subtraction first and then do exactly what we've been doing. Okay. So the first thing we would do is find the mean, the standard deviation, the t sub alpha over 2, and then your lower and your upper bounds. All right, so let's see. I believe I went from 12 to 21. This one wants a 90% confidence interval. So I'll use 0.95 for the probability and 9 degrees of freedom. Right? And then this one we'll just do what we've done before. We'll do the mean, which is B23. Subtract off the t, which is B25. Times our standard deviation estimate. Square root of B24 squared, and I'm just going to type in the divided by 10 in this case because I'm lazy. All right, so there is your lower and upper. And then again, the whole point of this is to make it a conclusion. Did the fitness program seem to help lower body fat percentage based on that output or that confidence interval? Is there evidence that it helped? No, because why? Good. Exactly right. The zero's in the middle, right? So there's not enough evidence to say anything, correct? The fact of the difference of zero being in the middle says that sometimes they gained, sometimes they lost, right? So there's not enough evidence here to say anything. I mean, that's one of the reasons why you use the confidence intervals, trying to make an inference along those lines. And I mean, that really is the whole point of this semester, is to try to do statistical inference. Based on a sample, can you make broad-based generalizations? In this case, no. I just did the males. You can do the females as practice and go alongside with it. Maybe the health fitness program helped females and not males. I mean, that would be one of the things you might look at.
Can you go back to the formula for either the lower or upper bound?
Sure. Can you see it at the top?
Yeah.
Okay. You're welcome. All right. So let's go on and talk about then the next section, unless there's more questions about that. All right, well, let's go on and talk about the next section then, which is confidence intervals for variances. So we want to do the exact same type of thing that we did for means and differences of means. Except now that when we're talking about variances, it's not a normal distribution anymore. The sample standard deviation, the sample variance multiplied by the appropriate constants is a chi-squared rather than a normal, right? So again, we want to do the same kind of thing though. We want, if I think about a picture standpoint, your chi-squared distribution picture kind of looks like goes up and then has a nice tail this way, right? If we want to have an interval of values where the likelihood that the true value had a high probability, you do the same kind of thing we do for a normal distribution. I've just got to split it at two different places, like say here and here, where this maybe is alpha over 2, and this is alpha over 2. So then the probability in the middle is 1 minus alpha. All right, so the notation for finding where these values are is chi-squared of alpha over 2 on the number of degrees of freedom that the chi-squared value has. Now, unfortunately, the chi-squared is not symmetric about some point, right? It's got a bump and then it tails off. So I actually have to find two separate values with these. This one, the notation is chi-squared of 1 minus alpha over 2 of r. We'll have to find both of them. Okay. Now again, for the r, we'll figure out what the r is here in a second, but this is what we're looking for, okay? So we want the probability, at the end, we want sigma squared to be in between two values, whatever they happen to be, right? That's what what's what we want to gun for. That's what it means for a confidence interval, right? We want it in between two values, right? So to get to this point, to figure out what the A and the B are, we need to go through that probability idea that we talked about with the normal distribution, right? We want that the probability that this is equal to 1 minus alpha, right? Whenever we get to that point. All right, so I'm not going to play much around with the right-hand side. It's going to be inside the left-hand side that we're going to play it with, right? All right, so I need to remember that if I do n minus 1 s squared over sigma squared, that is chi squared of n minus 1, right? Its distribution is. All right, so we need to play around with this and get to that point. So to get to this point, we need to reciprocate everything. When we reciprocate, of course, it flips the inequality. Right? We agree? Okay. So then I'm going to just rearrange things so that it looks more normal, quote unquote normal, not a normal distribution. Just rearrange the right things left to right, right? So I just flipped it around. Okay. All right, what else do we need? Well, I need an n minus 1 s squared on top, right? Right? All right, so if I do that, I would have n minus 1 s squared over b is n minus 1 s squared over sigma squared. And this is n minus 1 s squared over a. All right, so now I've got a chi squared random variable in the middle, right? I've got a chi squared random variable in the middle in between two numbers that I can calculate. Right? From a sample, I can calculate those things if I know what the a and the b are. Because if this is my chi squared random variable in the middle, these pieces here, if I'm going to cut it into an alpha over 2 tail below and an alpha over 2 tail above, this first value needs to be chi squared of 1 minus alpha over 2 on n minus 1 degrees of freedom. And this piece needs to be chi squared of alpha over 2 on n minus 1 degrees of freedom. It's those values, if I scroll, let me shrink it maybe a little bit. These two pieces here, I've got a chi squared random variable in the middle now. So these two values are corresponding up here, where we've got the alpha over 2 probability tail on the left-hand side and the alpha over 2 probability tail on the right-hand side. So those two pieces that are here and here have to correspond to those two fixed values for the chi squared that cut those probabilities off, like we had for the z's of alpha over 2 or the t's of alpha over 2. So now I can solve for a and b pretty quickly, right? Going back up to this original thing. So if I do that, your sigma squared then has to be in between. Solving this for a, your a has to be what? It has to be n minus 1 s squared over chi squared of alpha over 2 times n minus 1. And over here, it's n minus 1 s squared over chi squared of 1 minus alpha over 2 of n minus 1. Now, if this looks ugly, maybe not ugly, it looks complicated, it's really not. Here's why it's really not. It's the same thing on top, on both sides of the double inequality here, right? On both ends of the double inequality here. These values you're going to use Excel for, or your chi-squared distribution table for. You're going to divide this one by the bigger number and this one by the smaller number, because this has to be the smaller number. It's on the left-hand side, and this one has to be the bigger number, right? So as long as you can find both of these two values, you're not going to screw it up. You're going to put you're going to do your division. You're going to put the smaller number on the left and the bigger number on the right. I've been teaching long enough now that I get confused with left and right because I say left and right, and it's my right hand and my left hand. But looking out of the class, then I have to actually think about it for half a second when I actually do something. I need to left or right. Weird. But my brain's wired weird, which you probably already figured out. Mathematician, of course, it's like weird. We're all wired a little screwy. All right, so let's just do an example of how this works. All right, this is 6.4-3. So what we need to get the confidence interval here, we need first the, actually I'm going to go ahead and just do the sample variance because we're doing a confidence interval for the variance. So I can use the var point.s here for that command. And I've got this typed in from A1 to 825. Again, it's just whatever your size of your sample is. The next thing we need is, label that so you can actually see what it is. Sample size. I mean, I know there's 25 there, but I could use the count command to get it. Pardon me. Then I need my chi-squared values. I'm just giving them, there's two of them that you have to compute, so I'm going to call one low and one high relative to where they are on the graph. Does that make sense? Just as I'm just putting this in as a label. Okay. All right, so here's how you get them. One of the things I do like about Excel is when you start typing in a formula, it gives you hints for what you might want to use. Chi-square inverse dot right tail. Okay. One will give you the left-hand side that you need, one will give you the right-hand side that you need for the same probability. Okay? So in this particular one, let's use the chi-square inverse because that'll give you your left one, your lower tail. The probability that you want is, one's a 90% confidence interval, so we'll use 0.05 because we have to split the alpha in half again. Degrees of freedom. It's the number of things in your sample size minus 1. So in this case, it'll be 24. Okay. To get the higher number, again, let's just start typing it in there. We'll use the right tail one. Again, I mean, you could use the same one we did before. You just have to put in 0.0 or 0.975, or excuse me, 0.95. But again, if you use the right tail, we can just use 0.05 for both of them. And then it'll be C2 minus 1 again. Okay. So then when we do our confidence interval, again, to get your confidence interval, you're going to take your number of things in your sample minus 1, multiply it by your sample variance, and divide it by the bigger number, right? When you do this chi-square lower and chi-square higher, you're going to take the bigger number and divide it into the variance times the sample size minus 1 to get the lower bound. So we'll take this divided by C4. And for upper, you'll do C2 minus 1 times the variance, and divided by, and divided by the lower number, which is in C3. So this gives you a confidence interval for your variance. Okay? Like I said, the formula is not bad at all, is it? That's better than the last formula we just wrote down for Welch's T, right? Again, finding these are just using your chi-squared distribution functions that are built into Excel. Your formula that you use for, excuse me, not your formula, the variable that is a chi-squared random variable is n minus 1 times s squared over sigma squared, right? So you already have that n minus 1 s squared ingrained in your head, hopefully. It's just a matter of dividing by the chi-squared piece. And again, you're going to pick out the bigger one to divide it by. And then the last thing, if you want a confidence interval for your standard deviation, take the square root of both those numbers. That gives you a confidence interval for your standard deviation rather than your variance. Just take the square root of both of those bounds and you're done. Okay. It's asked for in one of the homework problems. You just have to do the square root of each number. It doesn't make it hard. All right. Any questions on that at all? I apologize for the technical difficulties there. Not fun. Okay. All right, so you got homework due Wednesday. We still have to talk about confidence intervals for ratios of variances, but we'll do that next time. I don't think that's in the homework, so that shouldn't be an issue. Anyway, have a good one. We shall see you.